Our next speaker is who is going to talk about cluster categories from generalized quivers.
Thank you. Thanks for the introduction. Thanks, of course, to Leuven and Emine for inviting me to be here. Like many of you, it's my first time in Bulgaria and quite enjoying it so far. Yeah, so I added the parentheses because as I was writing my talk, I realized that actually you can use thread quivers in the original sense, and I'll say what that means as we go along. So the first thing that I'm going to do is I'm just going to tell you what a thread quiver is, and then tell you two useful results of them. And then, so this first section is on arXiv, and like many things, when you start dealing with the continuum after you're used to dealing with discrete things, this took a lot longer than we thought, nearly 4 years. So the second thing I'm going to tell you about is this is work in progress. What kind of cluster categories we want and what we mean by a cluster category of a thread quiver. This from is very intentional. It's not of in the sense that you take some quiver and you get your cluster category in the classical sense, but it's from, and you'll see what the subtle difference is in a moment. And then I'm going to conclude at the end the shortest section with some cluster tilting subcategories, and then a remark about a restriction that we need here, and maybe some ways, or at least one way of working around this, and why we need these restrictions. So, and I'm going to try to sort of slow down a bit. I know it's Friday, we've been here for a whole week. Things are a bit, we're all tired. I should also say the notes, they're typed, so you can read them online, especially if you can't read my handwriting. But I'm going to say a lot more than I'm going to write down. But everything I say will be more or less in the notes that are on the website. So if you miss something I said, you can either ask me or you can move the notes. So thread quivers are originally an invention of Berg and Roosmalen. And I'm going to follow Bernard's convention at the beginning of the conference and tell you when preprints came out. This was 2010. And the point of their introduction of doing this was to classify dualizing K varieties, which they did successfully. But that's not the point of what we're doing with it. And then in this paper with Charles and Emine, we looked at a more general class of thread quivers than they did. So let me give you that definition. So a thread quiver is a pair. Well, you have to take a quiver to start that with this. And then you have some set P. And this is a disjoint union over the arrows of totally ordered sets. Just totally ordered. So this is a disjoint union, so we're not comparing different arrows or anything like this. It's just that for every arrow you have a totally ordered set. And couple things about when I say quiver, I'm not assuming finite, I'm not assuming interval finite, I'm not assuming any other conditions that one might normally assume for a quiver. At this point, I'm talking about a set Q0, a set Q1, and functions that pick out the source of the target, and that's it. As we need more restrictions, I will tell you what they are. But right now, Q is just any quiver. This, if Q happens to be infinite, it is important to make sure that this is set size. So for foundational reasons, you have to make sure that if you have infinitely many arrows, there has to be some bound on your cardinalities, because otherwise things foundationally start falling apart. So let's not do that. Everything is a set. And that was that. Okay. And then sort of a small sub-definition, or just sort of something to point out. If each of these P alphas is finite, then really you should be thinking of this just as some other quiver, right? So if I take A2, and then I put 3 vertices here, this, right, if I thread this arrow with a 3 element set, then I just get A5. It's just a movement. Okay. And then maybe I'll use this space for my example. I'm going to try to leave this off the whole talk, see how I go. But people have been talking about toy models. So let's have a toy model. And it's going to be this sort of strangely named so this is a D4 quiver, but I've named the vertices in a sort of strange way. 1, 4, 5 prime, and 5. You should think of this as a post set. 1 is less than 4, 4 is less than both 5 and 5 prime, but 5 and 5 prime can be comparable. So sort of the natural thing. And I'm going to call this arrow alpha. Yeah. And to make this a thread quiver, so this is my Q, I need to tell you what my P alphas are. And in this case, I'm not going to do anything with these 2 arrows. I'm just going to let them be. They're just still going to be ordinary everyday arrows. But this, as you might see by the fact that I've drawn it quite big, I'm going to do something with this. So it's going to be a union of sets. And so I'm going to take 2 minus 1 over n. And so this is going to get increasingly close to 2. I'm going to take the open interval in a real line between 2 to 3. And then I'm going to take 3 plus 1 over n, which of course is going to accumulate that way toward 3. So what does this look like? I will try to consistently use yellow for my threads. But in the middle here, you have this open set here. That's this thing. And then you have sort of this, not on the scale. You have these 2 things that accumulate for you. So this is sort of a graphical representation of what we're doing. And the idea is this whole thing is still a subset of the reals, so you can use the usual total order. And then this, I've intentionally designed it as an example, right? So that this just fits in between 1 and 4. And now you just take the same order that you had before. And this is also now a post set, where you just consider everything less than 5 to also be less than 5. Okay. Oh, good. So going back over here. I want another definition that's not particularly deep, but it's just a useful phrase to have. So if we have this, so we have our thread quiver from some thread quiver that we have, and we can create a subthreading. So each P alpha prime is a subset of P alpha with the usual total order and all this stuff. So if you have this, and the P alpha primes are all finite, then we call this thing this a finite subthreading. And so finite subthreading is also a quiver by this other remark that I made before. So this is just too fractional. And so the finite subthreadings are useful because if you understand the finite subthreadings, then you understand a lot more about the structure of the thread quiver that you're working with. Okay. So apologies for having sport. Actually, let me make a quick note. Every finite subthreading of our toy model is a type D n-quiver. So if we understand all the DN quivers, which we do, then we understand our thread quiver. And that would be the unity precise. Okay. But secretly, I'm just a category theorist who masquerades as a representation theorist. So what I really want to tell you is some category theory. And so category. Algebras thread quiver. Is it's given by the following, however you want to phrase this. The objects, this is always C, math cal C. So the objects are just your vertices along with all of your threads, as you might expect. The morphisms are A bilinearly generated by what's called path-like movements. What are those? So the first thing is you have paths in Q. So of course, if you want a path-like morphism, you need the original paths of the quiver. You're also allowed to move around inside of your thread. So you have if you take some x less than or equal to y inside one of your threads, then of course you can go from x to y. But with just these 2 points, you sort of have the original quiver happening and the threads are happening, and you need something that brings them together. So you're also allowed to go from anything inside of an arrow to a target. And of course, you can go from the source of your arrow to anything inside of your arrow. So now you can travel around your original quiver, then you can jump into an arrow and stop somewhere, or you can start somewhere inside of that thread, jump to the target of that arrow, and then move around inside the quiver, and then go to some other thread. So this really allows you to move around the entire quiver, thread quiver rather. And there are 3 relations. One of them is not really a relation, but an observation. But the first thing is eta xx. We're going to identify that with the identity on x, otherwise it doesn't make any sense. If you pause somewhere inside of your thread, then that's okay. You can go from x to y, y to z. That's the same thing as going from x to z. So inside the threads, they are completely totally ordered, and so that total order means that we shouldn't consider this composition to be different. And then, for those of you who are paying very close attention, if you go inside an arrow and then back out, this should be the same thing as just doing the arrow. Right, so if I go from the source, I go to some point in the thread, then I go to the target, that should be the same thing as if I had just done that arrow to begin with. So we don't want to introduce any new information other than the threads themselves. Okay. So here in our split model, Actually, let me give this model a name, which I will say very suggestively called A. And then you take columns in the path category are isomorphic to either the field that you're working over, if X is less than Y, or 0. Throughout this talk, K has whatever properties you think it needs to have. It is a field. If you think it needs to be algebraically closed, then it is. If you think it needs a particular characteristic or doesn't need a particular characteristic, then it does or does not. It's whatever field that you think is necessary. If you want to just work with the complex numbers, you're welcome to do so. Yeah, do whatever you want. Okay. So now,
But equally well, there is a category with no field. Equally well, there is just a category.
Yeah, so you could do this. You could just take the path like morphisms that are described with these relations and just leave it. And that would also be fine.
One
But
question about your toy model, take some point in the middle of alpha.
yep,
Is there a path to 5?
yes. Because you go from the point in the middle to 4, and then you take the arrow in the original quiver to 5.
Where was that in your list? Is that the problem?
So the the third item lets you go from X to the target. And then the first item is just adds to the cube.
And you can propose.
Yeah, so they're all K by linearly generated by these morphisms. The actual proper definition and construction is like 2 pages. So I'm suppressing a lot of the technicalities because anything beyond this is not quite enlightening, I don't think. Okay. So I said I masquerade as a representation theorist. I should probably tell you what a representation is, and you're not going to be surprised. Representation of the path category is just a functor. Unit vector spaces. And when you work over the continuum, you never, ever deal with the big module category because it is a nightmare. It's not even hereditary. So instead, you say M is pointwise finite dimensional if n factors to the root finite dimensional. So I'll use this convention of big V is all vector spaces, little v is finite dimensional vectors. If you want to know more about that hereditary stuff, ask me later, but it's sort of a weird thing phenomenon that happens. So, are there any questions up to this point? Because now I'm going to start stating other people's results and our results. Okay. So in 2018, there was a paper that appeared on arXiv that says all pointwise finite dimensional representations of a small category decompose into indecomposables. On the board, I'll write in the usual way. I'll say what that means in a second. So what I mean in the usual way, I mean that the decomposition is unique of the isomorphism and permutation of summands, and that each indecomposable object has local endomorphism ring, meaning the pointwise finite category of pointwise finite dimensional representations is called Riemann-Schmidt Hausmeyer. The sums might be infinite, right? So you need Hausmeyer's Riemann as well. Okay. So this was a very nice result, but also by himself. I think this was 24. Yes. Bill proved that all pointwise finite dimensional representations of a totally ordered set decompose into a barcode. what is the barcode? Totally ordered set is type A, basically. And so a barcode is just a direct sum of interval representations in the sense of a type A representation. So basically this theorem says that actually representations of any totally ordered set, the pointwise finite dimensional things are just type A things. You don't get anything particularly new in the pointwise finite dimensional book. So now, theorem, and this is one of the two theorems from the first paper that I will mention is yes. So well, you take a thread quiver QB and see its path category, and then the following are true. One is that every pointwise finite dimensional n decomposes as a direct sum plus some ni's plus a direct sum over the arrows of some n alphas. And so this decomposition, every n alpha is a barcode over p alpha, which probably doesn't surprise you. Every n sub I, I'm going to use is in quotation marks. There's some functors pushing and pulling things around, but this is a representation of a finite subthreading. And then if you have finitely many vertices, then you have finitely many n sub i's, and they all come from a common. In both of these last points, the subthreading is not unique. It's just that it exists. So, okay, so what does this mean? This means that a pointwise finite dimensional representation of a thread quiver is some barcode on the arrows that we just call noise, that's the letter N. And basically we call this noise because it's not touching the vertices of your original quiver, right? Somehow you've chosen some important points of your quiver, and you'll want to allow some wiggle room between the arrows, or between the vertices inside the arrows, but this isn't even interacting with the quiver that we started with. This is just noise. All of these are related to finite subthreadings in your quiver. So these are really the things that you want to analyze and study. This is just all basic. So if we go back to our toy model, this means that all of our representations of our toy model are type D shaped. So if you think about type D, just sort of as a reminder, here you have the parts that are sort of just branches without, these are the indecomposables that ignore one of the two branching points, but not the other one. You have your stuff where it's dimension 1, dimension 2, and then it splits off into dimension 1 again. And then you have what I call the type A part, which doesn't touch either of the dimensions. And so this is what type G all-directed quivers look like for Dn, and it turns out the indecomposables for our toy model fit into this exact same structure with the hums and the x's that you would expect, but there's no tau. And there's no all-directed translation because you have a continuum of things, and there's no previous thing, there's no next thing. So you do lose all-directed. But yeah, our toy model is effectively type D. Okay.
You took the board up again.
So again,
And the board, bottom board. You only write on half of the back.
huh?
You try to only write on half of the back or half or otherwise.
Yeah, I know, but,
Sacrifice.
yeah, if I want to do my toy model, I need to use.
Yeah, well, that's on the top of it. That's fine.
Let's keep the toy model.
Yes, okay. Which one's the dry one?
The green one.
You can also use the eraser.
The what?
The eraser,
That's actually.
that's also, yeah.
So I'm gonna tell you one more thing about this original paper, and then we're gonna move on. So. We have another theorem. Actually, let me make one comment first before I forget. Everything up to the bottom of this point, you can also do with what we call weakly admissible ideals. But because we're going to work with cluster categories, I'm not going to define them or get into them, it's just that you can do the decomposition with weakly admissible ideals, which generalize admissible ideals for pathologies. So, the decomposition still works. Okay. So, if you assume that your original quiver is interval finite, that means that between any two vertices, you only have finitely many paths. So then you have these two statements. So if your quiver has no infinite paths, so think of like type A infinity, where the path just goes on forever in either direction. So if you don't have any of these, then the category of pointwise finite dimensional representations of your path category, this is hereditary. Okay. Our proof technique requires that you have this no infinite path thing. There is a paper that suggests that you don't need this restriction, but the result is not confirmed by peer review yet, so I'm going to just.
Sorry, what is the infinite path?
So it's sort of like an A infinity thing where you take a vertex, and then you just keep going and you don't stop. So if you can do this, then you're not in this. So this excludes the linearly oriented A infinity. And of course the dual limits as well. But even with infinite paths, if you take the things that are finitely presented by the representable projectives, so by the compact planes, this is also. And this is really the thing that. And so in our toy model, this is very much interval finite and does not have any infinite paths. And so the theorem applies. Both of these two categories for our toy model are very well. They're both very clear. Okay.
Do they have enough projectives?
That's why we need this no infinite path restriction, is so that we have enough projectives. That's exactly it. We have two types of projectives, not just the representable ones, but we're not going to use them in the talk. So, but this is by the representable ones. So it's a conference on cluster category, cluster algebras and stuff, so I should say something about cluster categories. And I'm going to point at our toy model to explain this. Accumulation points, even the informal definition in the notes is kind of wordy. So I'm going to kind of just point at this picture. If you think about all of these points that are approaching this open circle, this open circle is an accumulation point of all these 2 minus 1 to the end. They accumulate to 2, as we know, and then on this side, everything accumulates to 3. And every point in the interior of this open interval is, of course, also an accumulation point. It's just some subinterval of R, so they're all accumulation points. And so take so this sort of rusty brown color, these are our accumulation points of our twin model. Not all of them are objects of the path category, but they are the accumulation points. And we need to keep track of those. In theory, you could have accumulation points that are approached from more than 2 sides. Like if I had threaded both of these arrows and done something different here, we could have an accumulation point at 4 approached from 3 sides. You might have 2 arrows incoming in your quiver. You have an accumulation point in the middle. There's a lot of things that you could do, but you're not supposed to. So let me explain what that means. I call them transversal. And the transversal accumulation point means that it is a directed limit on one side, an inverse limit on the other side, and those are the only 2 ways you can approach the accumulation point. And so it's sort of like you're transversing through the accumulation point. That's the only kind that you want. You don't want any other arrows coming into your accumulation point. You basically just want this picture. And so you come into your accumulation point and then you leave. And there's a unique way to come in, and there's a unique way to leave. And that's what we want for the transversal ones. Of course, when the paper comes out, this will be much more formal, but this is sort of the intuition that we want to have. Yes. Okay. So from here on out, things are going to start getting a little fuzzy as we move further and further into the work in progress. And so what I say is true as far as we know, but of course not fixed. So just in this talk, this is not a formal definition. So I'll use quotation marks, not an underline. We'll say that QP is nice if Q has no infinite paths, if Q is interval finite. If you think hard, these are very different conditions actually. And the last thing we need is that all accumulation points of the thread quiver are transversal. So we don't have any weird accumulation points that are going to mess things up, is what this says. And so if we come back to our toy model, then our toy model is a nice thread quiver. At some point we'll have to choose a word for this, but for now it's just nice. Yes. So let's take a very brief category theoretic detour, because like I said, I'm really just a category theorist. So you take some triangulated category, which I will suggestively call D. And we're going to assume that D has a Serre functor, and you have, the usual thing that you want for the classical cluster category. And then we're going to assume that this is also triangulated. And we're going to assume that we have some subcategory L such that when you restrict F to L, you get this nice commutative diagram. Both of these also being triangulated. So this is a full triangulated subcategory closed under X. If tau exists, well, in this case, yes, tau does exist. It's closed under tau, closed under hom. Basically, this is completely self-contained. If you have this, you can go this way, and you can invert all the morphisms whose cone is in L. And then this will also be triangulated. You can do that down here because this is triangulated, this is triangulated. So you can invert all the morphisms here whose cone is here. And I'm going to sort of spoil the surprise by just skipping the whole the thing, but then this becomes effectively, using a little bit of quotation marks to hide the technicalities here, but then this is also triangulated. And what's happening is that this is a Vernier quotient. It's not really a quotient, it's a localization. And it turns out that these kinds of localizations can be before decay, which is convenient. So that means that we can use this sort of setup for our project. Okay. So to do this, I will try not to write all the way to the bottom this time.
Just look the backboard up higher.
Ah, yeah.
Yeah. Good.
Okay, so we have a construction which is laid out in detail in the notes, but I will suppress almost all of the details here. If you have a nice thread quiver, then you can construct what's called the discretization. And the discretization, the summary goes like this. Every accumulation point becomes a copy of the integers. Everything else stays the same. So this is now a thread quiver. That was considered by Berg and spawn. And so the idea is now we can use their very nice theorem that says that if you have one of the very thread quivers, that means you have a dualized from K variety. Among other things, this means that yes. So you get this new path category CD, just in case we choose what this occasion later. You put a superscript G on the category and not all of the sets. That means it's discrete. So the nice thing is, this means that we can pretend that this is the small category. It's not, it's skeletally small, but we can pretend that it's small. You might see where this is going already. So now we have the boundary derived category of our original thread quiver. This is from the finally presented stuff, right? We want something we have a lot of control over with enough projectors and it's hereditary. This thing includes into the boundary derived category here. It's not from the usual thing that you might think. It's not a functor that involves these two categories. It's a functor that is defined on the boundary derived categories. And then you can, there's some L here that exists. I'm not going to tell you what L is, but it exists. And you can take this quotient.
The boundary derived category is the boundary derived category of this.
Of the percentage representations. Yes. So this allows us to leverage their theorem and then also your result down the bottom. Okay. So here we do have quotient. So where is the year? I have this written down somewhere. Yes. Do you know which year this preprint went on? The orbit categories?
2004.
Okay. We'll say 2004. It is in the notes. I just can't find it. So this thing is triangulated and behaves the way that we want. So is this thing, which I'm just going to call P over F for now. And the result that Charles and Emine and I have provisionally is that you can go, so this is iota, this is pi. We're going to use this later, this is pi bar. This thing and this thing are equivalent. So this is the quotient by L, and it turns out we can go back. And then now if you go through this whole loop, it's an autoequivalence. And if you even stop and pause at F, that is still an autoequivalence, which means that you get this. So if you go through and you go through F and you come back, you get this thing, which is equivalent to this thing, and this thing by a detour is triangulated. So now we have a triangulated quotient of the boundary derived category of a thread quiver, as long as the thread quiver is X. And that was the main thing I wanted to say. And in the last couple minutes, I just want to say a couple words about cluster tilting and subcategories. Or rather, not having cluster tilting subcategories. Are there any questions? So I'll just summarize what I said real quick. So this is the important thing to get out of this picture that you guys have been trying to do. But we're going to work with this B mod. So when I said cluster categories from thread quivers, the reason I said it that way is because we really want to work with B mod F. It's nice to know that this thing is triangulated so that somehow we're getting the correct kind of category, the correct kind of quotient, etc. But this thing is not pleasant to work in. This is first technical nonsense is all I'll say. It's nice to have this high bar quotient. And so what we have is we have a definition of something called weakly contravariant, the finite. We have weakly covariantly finite, and then we have weakly covariantly finite. And in the interest of time, I'll suppress the definition, but they are in the notes. And then we have this nice proposition that if you have some U in the upstairs cluster category, I will just now start writing, it's a cluster category, is weakly functorially finite if and only if I bar of U. So I'm taking U inside the cluster category here and I'm pushing it down here. If and only if this thing is actually functorially finite downstairs. So somehow we understand when these things are functorially finite. And this proposition is why we want to work with B over F, not with this. And so I'll say this is a provisional definition. We say that some T bar inside what I'm now calling the cluster category. Oops, there's no D. I'm calling this thing the cluster category. This is cluster tilting. If two things, T bar needs to be equal to I bar of some T, where T is cluster tilting in the classical sense. So this is the cluster category from like one March Todorov on arXiv 2004. And so this has to be cluster tilting in that sense. And so the first requirement is that this has to be the image of a cluster tilting subcategory, and pi bar inverse of pi bar of T is weakly functorially finite. So once you take everything that's quasi-isomorphic to T, that has to be weakly functorially finite. And so this is what we would like to say is cluster tilting. In the examples that we've done, including the full example, the cluster tilting subcategories do behave the way that you would expect. And not in the sense of like XOR orthogonality, but in the sense that if you mod out that cluster tilting subcategory correctly, then you get a module category. Sorry, not mod out, but a cluster tilting subcategory. There's a functor from the cluster category into the modules of the cluster tilting subcategory, sort of in a classical sense, when you push it out by the right things, which is not traditional, but they behave the right way somehow. Yes, and I don't have time for the last remark, but it's in the notes. You can read it or ask me about it.
Right. Are there any questions? What was the last remark?
So the last remark is that, let me just look really quick. In 2012, Kyoshi and Todorov, my PhD advisors, they put up a continuous cluster category of type A, and we would like to be able to recover it, but there's these little naggy problems where you can't use A infinity as your thread quiver because it's not nice. And you can't just take, say, A2 and thread it with the real line, because that's also not going to be nice because you have accumulation points at the end that are one-sided. And so we have the workaround that is specific for type A, but it would be nice to have sort of a general construction that allows you to sort of work around this nice requirement. And one way to do that might be to take subcategories of half categories of thread quivers, but that is something that Emine and her colleagues are working on. So we have to understand more of that before we can use the here.
Any other questions?
One quick question. You just take the real line, full real line, representation of the real line, but the field was one of the basic examples. Do you consider that an example of your thread quiver or not?
Yeah, you can consider it as a thread quiver by taking the integers A infinity and then threading every interval with like I to I plus 1 threaded with the open interval. And then the real line becomes a thread quiver in this way. But it's not a nice thread quiver because the paths go on infinitely in both directions.
You can't do it A2. That's different.
Yeah, exactly.
All right, no other questions. Let's thank Daisy again. Back at 11:30. I'm not in this stuff, but I got it.
Yes.